Simons. I'm a field engineer there. We kind of work, we straddle the go-to-market, which is the sales group, and the engineering group, basically act as go-betweens. And I'm one of the tracing subject matter experts for Grafana. And today, we're going to go through what tracing is. But to start with, what is tracing? We have to go into observability a little bit. And to understand where tracing fits into this, I'd like to kind of bring up these four different signals, which are basically the known OpenTelemetry signals. So metrics is probably the most well-known. Metrics essentially says, is something happening? And the way that we kind of look at is something happening is usually via things like graphs. So maybe some of you heard about the four golden signals, which Google has for its SREs used to determine what's going on with metrics. Grafana uses RED, which is also used by other companies, and that's rate of requests coming into a system, error rates of those requests in a system, and duration of those requests in a system. And generally, kind of like on the graph, this one is on latency, line go up, things go bad, requests are taking a long time, line goes down, things are good, requests are taking a shorter time. So metrics are usually the first line of defense for observability signals to see what's going on. Then we have logs. Logs are atomic events of things that are happening in your system. So log lines get generated one after the other chronologically, and that kind of tells you what is happening in a system. So, you know, we've had an HTTP request, an HTTP request is filled. Okay, well, we failed on the log line there, there's missing E anyway. But that's kind of the events that are happening in your system to tell you what is going on. And then we kind of move on to traces. And traces are more kind of, where is it happening? So in a system, we've kind of been sold this lie over the last kind of the previous 15 years that monoliths are bad, microservices are good. But the problem with microservices is now you have lots of little services that are kind of all doing different things when a request comes into a system and then you get a response back out. So we need to actually figure out where in that system, where in those microservices something is going wrong. And that's literally where traces come in, and that's kind of what we're going to get into today. Where in the request throughout those microservices is something going wrong. And then finally, just to round it out, we also have profiles. And profiles are essentially when you look into your services, take an individual service which is running as a binary or a process and figure out where something might be going wrong there. Usually this is because a service might be taking an awful lot of resources, maybe it's using a lot of CPU, maybe it's using a lot of memory, and profiling gives you things like flame graphs which show you exactly what's going on in any particular request at any particular point in time to give you a good example of where resources are being consumed. Traces and profiles tend to go together a lot these days, but we've only got 30 minutes, so I'm going to get into what traces are. So a trace is made up of one or more spans, and in this particular example, this is a trace, and every single of these horizontal bars up here is an individual span. On the left, we have the service name where that span occurs, and then to the right of that, we have the name of its span. And this basically builds up a model and a representation of what is going on in your services. So a span represents just a unit of work. And this could be anything. This could be from doing some processing on data. It could be carrying out a cryptographic hash. It could be calling another service downstream. Any piece of work that we kind of want to assign something to, we can make a span out of. So if you take an HTTP service, somebody maybe wants to add something to their cart on a shopping service. The user makes a request. It says, please add this, I don't know, rubber duck into my shopping cart. It hits the API server. The API server might go down and start talking to a catalog server. Do I have any rubber ducks? That's a piece of work. The catalog service will be looking at a database. How many rubber ducks do I have? That's a piece of work. You can turn that into a span. And then let's add that rubber duck into the cart so that we can pay for it. That's a piece of work. And now finally send a response back to the requester. Yes, you have a rubber duck in your cart. Each of those things is a span. It's a unit of work. Spans have hierarchies. So as we can see here again, we can see by the indentation here that every span here is a child of the span above it. So it's a fairly simplistic trace because it's just a cascading waterfall, and we can kind of see that the load balancer service then has another span in here which is decoding a get. That then works out that it has to talk to an API service, so then we have the app that is working out what it needs to do. It decides it needs to create a client so that it can then call a database underneath. The database goes away and gets some data, it responds, it keeps sending it back up the chain. And basically the length of a trace here is represented by the root span. So request data comes in, data goes out. And it's basically waiting, the length of these spans are essentially waiting for spans underneath to complete before they carry on. Now what I've just said is very simplistic because as you can actually see, this top root span
request comes in at 0 nanoseconds, it goes out at 5.16 milliseconds, but we've still got a span underneath, and the trace itself is 5.35 milliseconds.
Well, that's because what we're actually looking for is a request coming in and then a response going out, and that's what the root span is. But there may be other work that is going on that you've started in your different microservices that actually needs to be carried out until the end of it. So this could be cleaning up some data at the end here, and this is why it's taking longer. It might have responded to its previous parent span, its previous piece of work there, and sent some data back, and then this sends data back up here. But that might be cleaning up a connection. Similarly, down here, you can see this takes quite a long time. It's longer than its parent, probably because it's cleaning up the database pool connections that are going on. So basically, a trace doesn't particularly ever have to end. It can go on forever. You can keep adding spans, but really what most people are interested in is how long did it take between that request coming in and the response going out. So now we can kind of visualize what a trace looks like and what spans are. We can kind of get an idea, actually, that maybe there's something going on in the load balancer for a really long time, because half this trace is it working out which app to talk to. And then even in the app, we kind of take an awful long time to kind of do some processing before we then start to call the database to get some data in the first place. Maybe we can optimize some of this code. We're seeing immediately that things are taking longer than maybe they should. And that's where traces come in, seeing the latencies of things, seeing where errors are occurring. Now, for distributed traces, this needs traces to kind of propagate from one service to another. As one service calls another downstream, you need to continue that trace, because usually in a process in a binary, you've got so much information, you're going to lose that information as soon as you call another binary, another service downstream. So we have to ensure that we send the context for a trace to the next service. So this is called propagation. And in this example, we have a root service here, A, maybe this is where the request comes in, and it then needs to go and talk to several different services. It talks to service B and service E. But to ensure that service B and service E can actually also be represented in the trace, we have to propagate some data. And the way that this usually happens is whatever the tracing instrumentation that you have is working on, it will send a trace ID, which is the trace that the spans belong to, and it will send the ID of the span that is calling the downstream service. So this is the parent for the service that is being called downstream. So with these two pieces of information, we can ensure that we can actually get a trace that works across several different microservices without breaking that trace up, and ensuring that you can see traces from different services. And again, every single service in a trace diagram is usually denoted by a different color. So we can see that we have service A called service B called service D called service D called service E. So we've kind of gone into traces, we've gone into what spans are, the units of work, but the real depth of observability, the real magic source to traces are the span metadata. So spans themselves are the real meat of a trace. The trace, as I've said, it's a UID, but it basically is just a UID that collects a load of spans together. It's just a grouping. So most spans will include a status, and the status is, did the unit of work work? Did it fail? Did something else happen? They include events, which can be little bits of sub-work that is not useful for a span, but actually does allow you to see that other things are occurring, and we'll get into that in a little while. But the most useful thing about any span are these things called attributes, span attributes and resource attributes. And they are contextual pieces of information that actually say, well, what was the work that I was actually doing? So in the case of an HTTP call, for example, maybe you're getting something from a different server, it will include things like the HTTP method that you used, the status code when it got a response, in this case 200, everything was okay, the HTTP URL that you were actually sending data to, all of that kind of stuff. And that means that when you look at a trace, you actually get contextual information about what that piece of work was doing, and you can immediately understand what was it doing, did something go wrong, why did it go wrong. The other thing is a resource attribute. These tend to be other attributes that don't actually pertain to the work itself, but more around things like what was the name of the host I was running on? Was there an IP address? What was that IP address? If you're running in something like a Kubernetes cluster, what was the namespace name? What was the cluster name? All of that kind of stuff. So again, that gives you more infrastructural information about exactly what was going on and where. Okay, so we've lightningly gone through a trace, we've gone through spans and contextual information on spans. And we're going to talk now about the 4 stages of an average trace pipeline. The first is client instrumentation. So to ensure that you can actually get traces out, you need to take a service and you need to instrument it. And that's basically changing the source code in some way to output trace telemetry. The second is optional. This is a pipeline stage. And this is where you send trace data from those services, usually to a local collector, which will take spans that are coming in for a particular trace, and then they can do further processing on it before they send it to a trace storage. In Grafana's case, we have an open source engine called Tempo. That's job is literally to store traces and then index them so that they can be retrieved later by something like Grafana itself, which is a dashboarding tool which allows you to go away and get telemetry data. So those are the 4 stages. So before we go into instrumentation, there were a couple of really good talks this morning on OpenTelemetry, and we're going to kind of go into that because OpenTelemetry is becoming really, really big for the observability world as a whole. It's a CNCF project, that's a Cloud Native Compute Foundation project that basically encompasses the requirements for all sorts of telemetry, mostly again metrics, logs, traces and profiles. It's been developed and overseen by a large number of different players in the observability space. We've been contributors to it. Splunk, Amazon, Google, Datadog, a huge number of different people have all contributed to this. And the general idea is that it's meant to be an agnostic platform. You can add all of the telemetry via OpenTelemetry to your instrumentation, I can't talk, it's Sunday afternoon, instrumented services and applications, and then it doesn't really matter where you send them on to. If you decide you want to change vendors, if you want to host things yourself, if you want to do your own kind of telemetry backends, you can just keep everything that you've already instrumented and send it onto that. It means that it gives people a lot more flexibility in where they send their data. It defines something called the OpenTelemetry protocol, which is OTLP, and again, that allows it to send data around without you having to use a proprietary agent or a proprietary protocol. And it also includes SDKs for popular languages, things like Java, Ruby, Rust, Go, Node, all of that kind of stuff. There are loads of different SDKs that are worked on by a lot of the community, which means that APIs are consistent. So you can use the same APIs for generating telemetry across all of your different applications, no matter what the language that you've actually based them on is. Finally, it includes an OpenTelemetry collector, and the collector, as I've said in stage 2 of the 4 stages of telemetry, will basically collect any of that telemetry in your services, in your applications, and then start to process it before it sends it out to a final trace store, metric store, log store, whatever. The OpenTelemetry, the tracing component in OpenTelemetry is extremely robust. It actually came out of something called OpenTracing. OpenTracing has been around for a very long time, and basically OpenTelemetry took it in just wholesale, made a few changes, kind of aligned it with the rest of the signals as well, so that various different schemas were aligned, but it was the first thing to come out that was stable, and because of that, OpenTelemetry tracing is extremely stable. It also includes functionality such as sampling policies, batch processing, and a load of other different plugins that pertain to all of the different telemetry signals, which allow it to make it really easy just to kind of work with the data that you're sending it. And that's what we're going to kind of talk about for the rest of this. Whenever we talk about tracing now, my assumption is that we're going to be using OpenTelemetry in some way to instrument and process that data. So let's get into instrumentation itself. There's a couple of ways that you can actually instrument services. So the first is manually. And the way that you would do this is that you would yourself go away, or your development teams say, okay, I've got my code, I know that it does various bits of work, and what I want to do is ensure that I'm going to create spans for each of those pieces of work that marry into a single trace. So to do that, you would go away, you would change your source code, you would manually start traces, you would add spans manually around pieces of work, functions or for loops or whatever you want to do, add attributes that go along with that so that the spans that come out the other end are able to be processed later on. It's not a particularly difficult task, but it is laborious, it's time consuming, and it can put you in a position where it takes an awful long time to go through all of your services, especially if you've got a really big application, and put all of this telemetry in. As an example of this, here's a little bit of piece of code. It's really, really simple. All it does is it makes a request to a downstream service. But to manually instrument it, we call in a tracing library. I've simplified that hugely. You'd probably call about 5 or 6 different OpenTelemetry libraries. That would bring all the bits and pieces you need in to start creating traces and spans. But when this function is called, we start a request span. We call it downstream request. This will add it to any trace that is currently in progress. If there isn't a trace, it will create a new one. We then create a new trace context. You don't have to worry too much about this. All this is doing is saying any of this piece of work within these curly brackets, these braces, this local closure, that pertains to this span. So then we create some headers inside there
This is going to propagate the trace ID and the parent span ID, which is going to be the span ID generated by this request span, down to the next service when we call the request, which is basically just an HTTP request, in this case to HTTP bin. We send the headers along with it so that we can propagate the trace if we want to. That will come back. We'll set the status saying, okay, everything was fine, so now we've set the status on the span, your work successfully concluded, and now we'll end the span. Okay, that's quite an awful lot of work for that piece of code. And that's one of the first key problems that instrumentation has. If you have to manually instrument everything, it tends to put people off. So, I forgot about that, don't worry. Okay. OpenTelemetry came along with auto-instrumentation. Now, the idea with auto-instrumentation is that instead of having to go away and manually instrument all of your services, instead, the SDKs come pre-instrumented for a lot of different frameworks. So not your code, but what they will do is they will do things like, okay, there are common HTTP libraries, there are common server libraries, there are common Postgres libraries, any other sort of database libraries. So the idea behind auto-instrumentation is that the people usually who have written those libraries, those third-party frameworks, have actually instrumented it themselves, or community members have done so. So instead of you having to go away and actually instrument all of that yourself, you can rely on OpenTelemetry's auto-instrumentation to create traces, to create spans, to do all of that kind of work so you don't have to. Of course, for your own code, you would still have to do that. But the general idea behind this is it greatly simplifies the process of instrumenting anything. It also handles downstream service propagation. So if you are calling things like other HTTP services or via gRPC, instead of you having to go away and add the headers to do that trace context, that trace ID and that span ID, it will automatically do so in any HTTP call, in any gRPC call, without you having to do it. It is completely transparent. It will also add, as I say, when you're using these third-party frameworks, it will add relevant span attributes and resource attributes as well. So that means you don't have to worry about saying what the context was, what was I doing, what were the URLs, what were the methods, etc. All of that will be done for you. So if we go on to an example here of using auto-instrumentation with the same function, I don't require a trace library. I'm just making a request, and all I'm doing is making a call to the downstream service, because the OpenTelemetry SDK will do all of that for me. So I haven't had to change everything. I've been able to just automatically use auto-instrumentation, and it's done all the work for me. But how does it do that? This is where zero code comes in. So the general idea behind zero code is, instead of you having to, include in your source code even just a couple of OpenTelemetry libraries so that it can start doing that work, instead what we do is we change the execution parameters of the code as it starts up. So in this particular example, we've got service A, which is a little Node.js service, and service B, which is a Java service. But the way that I've actually instrumented using the OpenTelemetry SDK is all I've done is I've changed some environment variables. So I've given the Node.js service basically a destination. I'm going to call the collector. It's just a local service name is collector. And when I start up my Node application, I just carry out a require. So this is a global require instead of doing it inside your code. And it just says pull all the auto-instrumentation applications in, register it for me automatically, and then run it alongside my process. Now, as every other library is required into my code, it will add hooks to all of those things that it knows about that already have instrumentations for it, and therefore when my own service code starts calling these instrumented libraries, traces will automatically be created, spans will automatically be created based on the context of those libraries and those frameworks. And even better, when I then start making HTTP or gRPC calls to my second service, they'll automatically be added all of the span propagation context, so I don't have to worry about any of it. Similarly down here, my second service is in Java. There's a slightly different way to do this. In Java, you can have a jar agent, and what this basically does is say, when I start up my Java application, there's an environment variable called Java Tools Options. This points to the OpenTelemetry Java agent, and so when we start this up, it just basically starts using all of that again. It will add hooks to all of the JRE. It will start to add all of the spans, all the propagations that you need, and you haven't had to change anything. And that's basically what loads of people use now for OpenTelemetry. Start with auto-instrumentation and zero code, and then you can start using the SDKs if you need to pull it in, to add that extra workload, to add those spans, to actually perform on your code as well. So, as we're creating all of these spans, what are best practices around them? Well, if you're not relying on auto-instrumentation and you're doing your own spans, make attributes informatively searchable. You want to ensure that you're doing things like this. You want to add all the context, so for HTTP calls, methods, targets, URLs, all of that kind of stuff. You want to also ensure that resource attributes, and they're kind of down here in the net dot section, are also very useful. It's great to know where in your machines, what machine was using which service, is there something wrong with it, same with Kubernetes nodes, all of that kind of stuff. If you put resource information in, it will give you more context as to where things in your own infrastructure are going wrong. Then there are things like span events. We talked about them briefly earlier, but a span event is something which, again, is a unit of work, but which you really don't want a span itself for. So a really good example of this, these are the little white lines on these, would be a DNS lookup. I don't really care what's happening, but it would be useful to know if I'm calling a downstream service, but I need to do a lookup. When did a connection get open to the DNS server? When did I send an A record? When did I get an A record back? And when did I close the connection? Span events let you kind of add this extra detail, which you have which you might not have any control over. I can't control the underlying DNS server and client, but I can see what was going on and where. So this brings us on to collection. We've instrumented our code, and now we're going to work with it in a collector. So trace collection agents are basically processes that you run locally, and they receive all of the span data from your traces that are coming in. There's a couple of reasons for wanting to do this without just sending it to a backend store. The first and major one is batch processing. So if you are sending to a third-party vendor over the internet, what you don't want to do is be opening and closing connections all the time and sending bootstrap data. So what the collector does primarily is batch all of these up. It will batch these up into a certain size of data, and then it will open a connection, transmit all of this data, and then close it. And that makes it a bit more efficient. It means your egress costs go down. But the other thing it can do is it can also work on the data that you've already got. So examples of this are attribute mutation. Maybe you're receiving spans and they've got lots of great contextual attributes, but maybe there's too much of them. Maybe you actually want to rename them. Maybe it doesn't conform to the schemas that you have. Maybe you want to put schemas in. So the trace collection agents can also then go and say, okay, well, if I find a span attribute called this, I can rename it to this, or I could drop it if it's not very useful, or I could drop spans if they're not very useful. So it allows you to do a lot of pre-processing before you send that data to a backing store. The other thing that it allows you to do, and these are just a couple of examples, are things like tail sampling. So tail sampling looks at spans that are coming in for a trace, and then makes a decision on whether you want to keep them or not. Well, why is that useful? Well, that can be very useful in situations where you have thousands or hundreds of thousands of requests a second coming in, and producing a trace for every single one of these requests is just going to be a huge amount of data you're probably never going to look through. So tail samplers basically allow you to implement policies, and a policy, for example, could be probabilistic. Save one trace in every 100, because that just gives me a baseline of what is going on. But that's great, but what if errors happen? Well, you can add another policy that says, but if an error happens, save it always, no matter what. If the latency is above 5 seconds, that's a really long call. Save that no matter what. So tail sampling allows you to actually make those decisions, throw away traces that aren't going to be of any use, and then send those traces that are to the backing store. The only thing with tail sampling is that because it has to look at all of the spans that are coming in for a trace before it makes a decision, this can actually increase the resource usage that the collector is using. OpenTelemetry is a default of 30 seconds, so it needs to have enough memory, enough CPU power for receiving however many traces you're actually producing to be able to do that. There is actually load balancing in the OpenTelemetry collectors as well, and in Grafana Alloy, which is our distribution of the OpenTelemetry collector. So there are ways around that, but it's worth taking into account. I've kind of gone through the common sampling practices, so I'm not really going to get into that, and I am going over time. The other thing that a collector can do is things like tracing metrics. So again, metrics, what is happening? Traditionally, you've had to instrument your services to produce metrics. But the great thing about tracing is spans are showing you units of work that are happening in your services. So why don't we just use spans to create metrics? And that's literally what the span collector and the service collector in the OpenTelemetry collector spec do. They look at the spans coming in, and then they produce metrics based on them, and they add some labels. They add the service name, the span name, the status, and the span kind. And that gets you enough information to start getting those rates, those red metrics, those rates, errors, and duration metrics, so that you end up with something like this. And this is basically a set of panels that are based along metrics that are just generated via spans. So because of the way that I can actually start chopping and changing what attributes we use, we can get an idea of requests going in and the endpoints that they're using. We can do the same thing with errors. We can see the error rates that are occurring on particular endpoints, and we can look at the durations that are occurring as well on those endpoints, purely from looking at the spans that are being generated from traces. So you've instrumented your code, or you've used zero code. You've set up a collector so that it pre-processes your span data however you want it to do.
and then we have to send it to somewhere else. And in the case of a trace store, we have something called Tempo, which is an open source tracing database. What the backend does is just a few things. It groups all of the spans of a trace together so that when you want to retrieve it, you can use something like the trace ID, and it will just retrieve all of the spans that are associated with that trace ID. It will store the trace data and index the trace data in such a way that makes it very efficient and optimized both for storage, but also for retrieval afterwards. And it can do a few other things. Tempo also does things like metric generation as well. We're working on something called adaptive telemetry at the moment and adaptive tracing, which will do tail sampling for you at the back end. But trace engines in general are just there to store the data and then allow you to retrieve it. So finally, we're going to go into actually visualizing traces. I have a problem with my machine. I will warn you in advance. I have not been able to get this to actually just mirror a display, so I'm going to have to turn around and take you very quickly through, hopefully, there we go, a Grafana interface. So this is Grafana, and what we're doing here is we are, this would be the easiest way to do this. Let's move that. We are looking at a data source, which is the Tempo data source that I have locally. Okay, thanks, Mark. Let's run a query, and we have here just essentially all the latest traces that are coming into the system. So if I click on one of these traces, I can retrieve it, and now what I'm looking at here is essentially a trace that is posting data into a database. So at the very top, I have a service called the requester. It has been told, please post some data into the system. The type of data I want to send is this particular thing called a beast. It's beholder. It's a post because I'm sending data into another service. And I'm going to call the next service on the /beholder endpoint. Note that this is in blue. The next one is in cyan. And this kind of shows that I'm going from one service to another. So if I go into the server service, this is showing that it is taking that post request. It is coming in. It is listening on Mythical Server 4000. I'm receiving a post. This is the length of data. This is the HTTP scheme and so on. And then a couple of spans later, after it's done a little bit of processing, it then calls an underlying database, the Postgres database, and it shows me all of the work that it's doing there. So this is the connection string to the database. This is the database name. And this is the database statement that I'm actually using to insert that. So that's all very interesting. You can kind of see that all of this happens within about 312 milliseconds. But there's something else interesting here, which is that after we've actually got a response back and we've sent it to the requester, we see there's some other work going on here. So what's actually happening is the requester is trying to publish some data to a bus. But this is taking an awful long time. This is taking like 1.17 seconds. Now in a situation where I haven't instrumented anything, if I was using just kind of like K6, which is our load testing application, or any other sort of like curl-based testing, and what are the timings for this? Okay, well, I'm getting a request back in 312 milliseconds. Everything's running fine. What I wouldn't know particularly is that actually trying to then store some data to a bus internally is taking me an inordinately long amount of time. By putting tracing in, I can see that something is happening that is not related to the main thing that we're using the services for. And this is where the true beauty of tracing comes in. I can see everything that's going on, not just the obvious stuff. Going back to kind of like the example with metrics generation as well, we have a little dashboard down here. Because all of the data coming in from here is being generated from spans, I can also set Grafana to do a very simple set of data linking. So we've got some errors going on here, and I'd like to know, well, why are we getting errors on these particular different endpoints? So I've got a very simple data link. This will take me back to the Explorer window. And what it's going to do here is it's going to create some traceQL based off the fields that it was looking at for the metrics. Don't worry too much about this. TraceQL is Tempo's tracing language. It allows you to build up extremely detailed requests for exactly the type of traces that you want to look for. And in this particular case, I'm saying, well, please find me any traces where a single span has an HTTP target of illithid, because that's the thing that's going wrong, and has an error on it, because I want to see all of the traces that are actually erroring. So any of these traces now will show me, if I click on it and the trackpad works, one of these traces. And now this trace, again, very similar to the last, but we can see here there's a couple of exclamation marks, right, in these little red circles. And what those denote is an error. So if I look at one of these spans, we actually have a status here of error. So that's telling me, okay, well, immediately when you look at this trace, there are some problems going on. Now, because this is kind of a parent-child hierarchy in this particular trace, I can kind of get the idea that probably what's going wrong
is in this particular span here. And again, I can go in and I can look at the connection string and I can look at what it's trying to do. Okay, it's trying to insert data into a table with a particular column name. And again, this has got an error. Oh, but I have a status message. So because the Postgres library is all auto-instrumented, it's telling me what happened when I actually sent data in there. And in this case, null value in column name of relational if it violates null non-constraint. Now, to a lot of people, that's going to mean absolutely nothing. But if you're a DBA or if you're the person that wrote the service that is calling the database, you go, oh, I'm not meant to send null data into that column, but something is. And now I've immediately got kind of like an initial flag benchmark where I can go and say, okay, well, it's either got to be something to do with mythical server that's calling the database, or the database is set up incorrectly, or something around that is going wrong. And I can always go and tap the DBA on the shoulder and say, hey, what's all this? I've immediately gone from not knowing anything about why there's an error to really easily being able to find what's going on. And again, this kind of shows you the power of tracing. There was a ton more I could show you. I only had 30 minutes, and I think I'm almost spot on. So if we go back to there, the right one. What I've just been playing with is fully open source, and you can go and play with it yourself. That QR code will take you to the repository. It is a full introduction to metrics, logs, profiles, and traces in Grafana. It is fully open source. It has a couple of demo services which are fully instrumented, both manually and auto-instrumented as well. It has a full OpenTelemetry collection pipeline. There's an OpenTelemetry collector, and there's Grafana Alloy, which is our version of the OpenTelemetry collector. It has a load of dashboards, and it has a fully commented set of source code and config. So if you're interested in learning more and you just want to go and download a Docker Compose set of files, that is the thing to do. Questions?